Now, our second workshop is presented by Mackenzie Simper. Mackenzie is finishing her PhD at Stanford University in mathematics, and it is advised by Percy Diaconis. Her research area is applied probability. Mackenzie will be presenting today the workshop Intro to Markov Chains and Bayesian Inference, and she will be available to to answer questions at the end. Please welcome Mackenzie.
Hi, everyone. I'm Mackenzie. I'm going to talk about Markov chains, just a very high-level introduction, kind of more on the theoretical side, just defining Markov chains and what they are, and then show one specific application relevant to data science, which is in Bayesian inference. So if you've never heard about Bayesian inference, don't worry, I will describe how it works a little bit and talk about Markov chain Monte Carlo, which is where Markov chains come in and why they're very important and useful. And also talk about the Metropolis Hastings algorithm for Markov chains. So I'm hoping that I'll have time at the end for questions. So think about questions as we go along, and I'll try to get to as many as possible as I can at the end. Okay. So first of all, Markov chains, part one, Markov chains. If you've never learned about Markov chains and want a little bit more background and maybe some more background into probability as well, I recommend this book. There's lots of really great introductory probability books and Markov chains books, but this is one that I particularly like and has a lot of good exercises relating to Markov chains. Okay, so let me start with an example, which is a random walk. So suppose we have a number line, 1, 2, up to n, and I'm going to define a random process by walking, thinking about this number line as a sequence of steps. And basically how it will work is flip a coin. If it's heads, take a step to the right. If it's tails, take a step to the left. I also have to say what happens if you're at the end point. So if you're at position 1 and you can't take another step to the left, then just stay put with probability 1/2. Or take a step to the right with probability 1/2, and same thing at the other endpoint. Okay, so keep doing this and you're going to get a sequence of random numbers. Pick some arbitrary starting position. Maybe you start at 1 and then keep flipping a coin and record where you are at each time step. And this is a sequence of random numbers. And these random numbers take values in what we'll call the state space, which is the numbers 1 up to n. And the key property of this random process is that the probability of where the walker is going to be at the next step only depends on the current position. So it doesn't matter what was the previous sequence of steps to get to where you are now. It only matters where you are now to determine what's the chance of where you'll be at the next step. Okay, that's the crucial property. This is what we call a transition graph or transition diagram, which is just a nice pictorial way of representing a Markov chain. So here we have the 5 states, and you see if you're at 1, 1/2 probability of staying at 1, or 1/2 probability of going to 2. If you're at 3, 1/2 probability of going either left or right, and so on. And then this is just a plot of some sample paths of what this experiment, would look like if you did it a couple times, starting from 0. Different colors would be different random walks, because each time you're going to get a different sample path. So, and then this is time or steps. So you go up and down and back and forth, and eventually if you hit the boundary, you'll bounce back. Okay. So this is a Markov chain, and why it's a Markov chain is because it satisfies that key property that I mentioned before, which is what's called the Markov property. So a Markov chain with state space S is a random process which satisfies the probability of xt plus 1 being some value in our state space, conditional on all of the previous the path up to time t is equal to the probability of the next step, just depending on the current, think of this as the current position. So again, it doesn't matter what were all of the, what was the exact sequence of steps, no matter how you got to this point. In this, no matter how I got to 3, when I'm at 3, it's still 1/2 probability of going to 4, 1/2 probability of going to 2. Okay, so it seems simple to talk about, but this property is very nice, and it gives us a lot of tools for understanding this random process and thinking about different features of this random process. And this example with the random walk is what we would call a discrete time and discrete space Markov chain. So discrete time means that the steps are discrete, right? 1, 2, 3. And discrete space is that the state space is also discrete. It's finite in this case. But we could also talk about continuous time and or continuous space Markov chains. I won't talk about them today, just because it's a slightly different setup, but just know that they exist and have lots of different applications in different settings. Okay, so when we have a Markov chain that's discrete time and discrete space, we can talk about the transition matrix. So this is just a matrix which stores these transition probabilities. So it's a nice way of keeping track of the transition probabilities. This matrix stores all the information that we need to define this Markov chain. So K of XY is the probability that xt plus 1 equals y, given xt equals x. So here's the example for our random walk with 5 states. So we look at the first row. This is a probability distribution on the space, which is the distribution of your position at the next step if you're currently at position 1. So there's 1/2 probability of staying at position 1, 1/2 probability of moving to position 2. And then, looking at row 2, it's the probability distribution on the states at the next step if you're currently at position 2. So 1/2 probability of moving to 1, 1/2 probability of moving to 3. So it's exactly the same information I showed in that transition graph, just stored in matrix form. And what's really great about storing it in this matrix form is that we can use different tools from linear algebra to study this Markov chain. For example, if we multiply this matrix by itself, it's a square matrix. The matrix is always going to be, the size of the state space times the size of the state space. Those are going to be the dimensions. Then if I multiply the matrix by itself, t times, this will give me the t-step transition probabilities. So k to the t of xy is the probability that xt equals y given x naught equals x. So for example, here's k squared. Again, if we look at the first row, that tells me the distribution of the states after 2 steps if you started, x naught equals 1. So if you start at 1, then there's, after 2 steps, 1/2 probability of being at 1, 1/4 probability of being at 2, 1/4 probability of being at 3, and so on. You could have given this as an exercise for an undergraduate in Intro to Probability to calculate these probabilities by hand, just by thinking about the combinatorics and the different ways. If we're at 1, we could have just stayed at 1 for 2 steps, or we could have gone from 1 to 2 and then back to 1 and add up all those probabilities. But using linear algebra and taking powers of this matrix is a much easier and saves us ourselves a lot of computation to just take the matrix powers, and it gives all these probabilities. Okay, so that's very useful, use of the transition matrix. I wrote down what it looks like for a couple more steps. So this is k to the 3, after 3 steps, after 4 steps, and so on. So you see, you can kind of see the probabilities are spreading out. At first, if we started at 1, then after 2 steps, it's likely we're going to be close to 1 already. But then after 4 steps, if we started at 1, well, there's still the highest chance that we're going to be at 1, but now there's some chance that we've spread out more and we're at, higher numbers. So you might have the question then, well, what happens if I keep multiplying this matrix? What happens if I take the limit as t goes to infinity? So if I run the Markov chain a very long time, what will be the distribution on the position? It's like if you set the random walker, get it going, and then you leave, and then you come back, can you predict where the random walker will be, or what is the distribution, the probability distribution over the states? So that's something you might be wondering. And you also might be wondering, does that depend on what is the starting state? Whether you start at 1, 2, 3, 4, and 5, are you going to get a different limiting distribution? Well, before I answer that question, I need to define 2 more things related to Markov chains, just so that we're looking at Markov chains which are nice. So think about it, if a Markov chain satisfies these 2 properties, it's nice, and nice things will happen. So the first thing I need is that the Markov chain is irreducible. So being irreducible means that for every 2 states in my state space, there is a t such that kt of xy is greater than 0. So that means no matter where I start, if I wait long enough, there's going to be some probability of getting to any other place. Right? So for this example, we see, k3 of 1, 5 equals 0. So 3 steps isn't enough time to reach 5, but 4 steps is enough. And since now after 4 steps, everything in the matrix is non-zero, that certainly means this Markov chain is irreducible. I also have a picture of what a Markov chain would look like if it is reducible. Would mean that your transition graph has these 2 disjoint subgraphs. So in this Markov chain, you have 6 states, but it's really like 2 Markov chains within one, because there's no way, if you start at state 1, you can never get to state 4 or higher. So this Markov chain would be called reducible, and irreducible is if it doesn't look like this. There's no disjoint subgraphs. Okay, so that's property number 1 that I want to talk about. Property number 2 is that we want the state, the Markov chain, to be aperiodic. So a state is called periodic in the Markov chain if kt of xx is positive only if t is a multiple of some integer d. So I think that's easiest to see by an example like this. So here we have, this is the transition matrix. We have 3 states, and the transitions are from 1, you have to go to 2. From 2, you could go to 1 or 3, with probability 1/2. And from 3, you have to go to 2. So at first, this seems like a perfectly reasonable Markov chain, and it is. The problem is that there's periodicity in where you can be at certain times. So if we look at k squared, oh, that should be 0. If we look at k squared and k cubed, you see that the Markov chain starts to repeat itself. And if you start at position 1, for example, where you see that kt of 1, 1 is greater than 0 only if t is even, right? You can never be at position 1 at an odd step. You can only come back to it after an even number of steps. So there's this periodicity in the possible positions at certain times. And, you know, again, this is a perfectly valid Markov chain, but I want to assume that my Markov chain is not like this, assume that it's aperiodic, because you can imagine if we're talking about the long run probability, you know, what happens the limit as t goes to infinity? Well, it would be a problem if it was periodic, because then this result is going to depend on if t is even or odd, for example, in the example that we did. Okay, so those are sort of 2 technical conditions, but they're reasonable. You know, if you think a Markov chain that is irreducible and aperiodic is nice. And so if we assume those things, then something very nice happens, which is there exists a unique probability distribution, pi, which is what we call the stationary distribution of this Markov chain. Which satisfies these properties. So first of all, you know, the sum over all states of pi of x sum to 1, that's just being a probability distribution. But it also has positive probability, puts positive probability on every state. And then we have this long run or long-term limiting behavior that we were talking about. The rows of kt converge to pi. And, you know, I'll emphasize every row. So here, this answers the question of, does the limiting distribution depend on where you start? No, not if your chain is irreducible and aperiodic. We can solve for the stationary distribution using linear algebra, because it satisfies, if we think of it as a vector, then it satisfies pi k equals pi. So it's a left eigenvector of k with eigenvalue 1. Another way of writing that is that for all y in our state space, pi of y is the sum over x in the state space, pi of x, k of xy. So looking at this equation, I think it's intuitive to think about pi as a stationary distribution, which is if I sample from the stationary distribution and then take one step according to the Markov chain, well, then the random distribution of where I am after that one step is still according to pi. It's still following this stationary distribution. Okay. Right, so we call that stationary distribution. And as long as k is irreducible and aperiodic, it is unique. So for example, on our simple random walk, the stationary distribution is 1/5, 1/5, 1/5, 1/5. Everything has probability 1/5. This is called the uniform distribution because everything in our state space has the same probability. And we could just see that pi is a left eigenvector, right? If we were to multiply this vector by k, we're going to get back pi. So it satisfies that linear algebra equation I mentioned. It's a left eigenvector. Notice that this specific Markov chain, this random walk, which we call simple random walk, when the probability is 1/2, is even more special in that it's symmetric. So this means that the probability of moving from X to Y equals the probability of moving from Y to X. We're, looking at the transition matrix, it's a symmetric matrix. And it turns out that whenever you have a symmetric matrix, the stationary distribution is always uniform. So that's kind of a nice, easy, quick way of checking if your Markov chain has uniform stationary distribution is if it's symmetric. So here's an example of a Markov chain that's not symmetric, is if we change the random walk. So instead, it's going to step to the right with probability P and step to the left with probability 1 minus P. And P can be whatever we want in between 0 and 1. So then it's not symmetric. For example, when P equals 1/3, I calculated this is the stationary distribution. So of course, the highest probability state is 1, which makes sense because, at each time there's 2/3 chance. There's much greater chance of stepping to the left than there is of stepping to the right. Okay. One more definition I want to talk about with stationary distributions and this transition matrix is to be reversible. So not every Markov chain satisfies this, but a lot of the nice ones do, which is a Markov chain is called reversible with respect to its stationary distribution pi if pi of x, k of xy equals pi of y, k of yx. So you can it's not as if the Markov chain is symmetric, but you can reverse it in some sense with respect to this stationary distribution. For example, this is a way of seeing that a symmetric transition matrix always has uniform stationary distribution, right? Because if the stationary distribution is just 1 over the size of the state space, then of course it satisfies this equation. And one reason I'm telling you this is because it's going to come up a little bit later as a way of finding a stationary distribution. So if you can find a function pi that satisfies this equation, then you know that it's your stationary distribution. So it's a nice condition to know about. But again, not every Markov chain necessarily satisfies this, but if it does, then you know that pi is your stationary distribution. Okay. Before I get to the data science and the Bayesian inference, I just want to briefly mention some of my favorite Markov chains. Of course, there are many, many out there, lots of applications. These are ones that I've spent some time thinking about. So easy one is shuffling a deck of cards. So when you shuffle a deck, that's random. If you do it many times and just keep doing it over and over, that's the random process. And it's a Markov chain. The state space is kind of interesting. It's the set of all permutations of n objects if you have n cards. So how many different ways you can arrange. Like in your standard deck of cards, you have 52 cards. So the size of the state space is 52 factorial. It's a huge state space. And then there's lots of different ways you could define a random process by shuffling cards. Riffle shuffle, which I won't explain now because it's a little bit complicated, but it is something that people have studied, is a model for how most people shuffle, splitting the deck of cards and then interweaving the two sides together. And you can formalize that as a Markov chain. Some other easier ones to describe would be random transpositions, which would be pick 2 cards at random and swap. So in this example, I have 6 cards. I swap, 2 and 5. And since there's 6 choose 2 pairs, possibilities for swapping, and I pick 1 at random, then this has probability 1 over 6 choose 2. Or, maybe even more restrictive, you could do it just adjacent transpositions. Pick 2 adjacent cards at random and swap. Both of these are symmetric Markov chains, so they have uniform stationary distribution. So if you do them over and over long enough, you're going to get a deck of cards that has uniform distribution that is equally likely. Another one that I like is what's called a coagulation-fragmentation model. So here you can imagine that you have n total particles grouped into blocks. So maybe like I have, 4 things there, 3 things there, and then 2 things there. At each step, pick 2 particles at random. You pick that one and that one. And if they're in different blocks, then merge the blocks. But if the 2 particles are in the same block, split apart the block uniformly. So this model has been used in population dynamics, thinking about the blocks as families. It's been used in physics, thinking of the particles as literal particles. And it's just quite a nice chain from a mathematical perspective to study. The state space is the set of all partitions of n. So like how many ways can you break apart n things into different size blocks? So let's see, I have an example here. When n equals 4, you could have them all the same block. You could have a block of size 3 and 1, 2 and 2, 2, 1, 1, 1, 1, 1, 1. And I won't go through how to calculate these probabilities, but it's just coming from the dynamics that I described. Okay, another one that I've worked with is looking at a Markov chain where your state space can be quite complicated. It doesn't have to just be integers, right? We've seen the state space can be all permutations, all partitions of n. Your state space could be something else, some other object. In this case, the set of all genealogical trees. So when you have n leaves, you form a genealogical tree like this that just shows the relationships between the leaves. And you can define a Markov chain that moves throughout this state space. So you move from tree to tree to tree to tree. And that's very useful in, again, population genetics. And it will keep this example in mind when I talk about Bayesian inference in the next part. Okay, so there are many, many more examples. Markov chains are used to model real processes like infectious disease models. This is a picture of the SIR model as a Markov chain, weather forecasting, stock prices. Some of these are going to be continuous time or continuous space processes. Another big application right now is to reinforcement learning through Markov decision processes. Another application computationally is using a Markov chain which has uniform stationary distribution. So again, this is where pi of x is just 1 over the size of s. For some state spaces, the size of the state space is actually very hard to count. Maybe, for example, coalescent trees or these genealogical trees. How would you count how many possible trees there are? That can be a very hard problem for some spaces. But if you have a Markov chain which has uniform stationary distribution, then you can estimate this S, this size of the state space by running the Markov chain until it converges to its uniform distribution. All right, that's just a sample. My point is, Markov chains are everywhere. They're very cool to study from a mathematical perspective and have many applications. Okay, so for the second last little bit, I want to talk about one specific application to data science, which is through Bayesian inference and through Markov chain Monte Carlo. So everybody knows Bayes' theorem, I hope, one of the most useful theorems in math, which gives the probability, conditional probability of two events, A given B, as the probability of B given A times the probability of A divided by the probability of B. Okay. I put a little example, oops, going through it, but I won't go through it now. If you need a little review, then you can work on that later when you have the slides. So Bayesian inference is a type of statistics. You know, it's kind of one mindset in statistics where you have D is your observed data as usual. And as usual with statistics, you assume that the data follows some model with parameter theta. So this gives you a likelihood, the probability of seeing the data given the parameter theta. And in statistics, what we want to do is we want to estimate this parameter theta. So what you might have done before is calculate, you know, the MLE, the maximum likelihood estimator, what theta maximizes this probability. The Bayesian approach is a little bit different, which is to instead assume that theta is some fixed value that we want to estimate, assume that theta is also random. And so we assume that there's some prior distribution, prior probability on theta. And then given the data, we can update this estimation using Bayes' rule, which gives the posterior distribution of theta. So the probability of theta given the data is the likelihood of the data given theta times the prior divided by this normalizing value, probability of the data, which could be calculated just by the law of total probability, you know, summing up over all possible parameters in our state space. Okay, you know, a very just super simple example of how this might go is suppose your data is a sequence of n coin flips and you want to estimate what's the probability of getting heads. So maybe it's not a fair coin. You could assume some prior distribution. Maybe you know that it's either going to be 1/4, 1/2, or 3/4, but you don't know, you know, what's the distribution on these. So you could assume prior is uniform. You could also do, you know, a continuous prior distribution, but just for simple example, just keep it discrete. So then the likelihood is the binomial distribution, right? Just if you flip a coin n times, probability of heads is theta. How many times do you get heads? That's that. And just plug everything in to get our posterior. Lots of things cancel out and you get something that looks like that. Super simple. In this case, it's very nice. You can write everything out. And you could simplify it even further than I did, but that's just to show you how it would work. So that was a very easy example, but the problem in practice is that this posterior can be intractable to explicitly calculate. And often the problem is that this factor, this normalizing factor, remember, which we said could be calculated by summing over all possible theta. This could involve a huge sum, a sum over a huge state space, depending on what our parameter is. So for example, in the example I mentioned before, where we had genealogical trees, if our data would be, think about it like genetic sequences from n cells, and the tree, the parameter theta is actually the tree itself. So we want to, you know, think about what's the most likely tree that would give this genetic data. Well, that's a huge state space. The number of trees in that example is like n to the n. So if you have a lot of data it's a huge possible state space to sum over. And it's going to be a big problem to explicitly calculate a formula. So what's the solution? Markov chains. We can design a Markov chain which has the stationary distribution, the posterior that we want. And once we have that Markov chain, we can run the Markov chain many times until it reaches its stationary distribution, and that will give samples from the distribution, which can be used to estimate the mean, the variance, whatever we would want to estimate about this distribution. This general process is called Markov chain Monte Carlo. Okay, so then your next question might be, well, how do we design a Markov chain which has this weird stationary distribution? You know, that depends on the likelihood and so on. Well, it turns out to be pretty easy as long as we have any Markov chain on the state space that we are looking at. And this is called the Metropolis Hasting algorithm. Very simple, but very powerful. So if we have pi is any probability distribution on our state space, and k can be any Markov chain. It doesn't matter what is the stationary distribution of k. It can be anything. We can use k to design a new Markov chain, call it k tilde, that has stationary distribution pi. So how this works is from the current state, take one step according to k. So, you know, just take one step according to your Markov chain k. This is what we call the proposal step. And instead of just moving directly to the proposal, we're first going to compute what's called the acceptance ratio, which is this weird looking formula, the minimum of 1, and then this expression that depends on our target stationary distribution and k. So this is always less than or equal to 1. So it's a probability. And with probability A of xy, we accept the proposal and move to state y. Otherwise, we're going to stay at state x. And this new Markov chain will have stationary distribution pi. It might be kind of weird to think about why that is just by describing this algorithm, but it's actually really easy to prove using what we talked about a Markov chain being reversible. So we want to show, you know, the stationary distribution is pi if k tilde, if pi of x, k tilde xy equals pi of y, k tilde yx. If we can show that, then we know the stationary distribution is pi. And that's very easy to show just by these probabilities, right? If x is not equal to y, then k tilde of xy, the probability of taking a step is first, you know, propose y. That's that probability. And then second, we've got to accept y. That's that probability. And then you can just do the multiplication, do the little algebra. You see that the pi of x, k of xy is going to cancel with that thing. Oops. And very simple algebra. It all works out. So this is sort of the magic acceptance ratio thing to multiply so that it works out and you get that it's reversible. So that's really cool. You know, any Markov chain, you can plug it into this algorithm and change it to be a new Markov chain, which has the stationary distribution you want. And what's really important for the Bayesian inference application is that if pi of theta is our posterior, which looks like this, remember this was the expression, then the acceptance ratio, when we plug it in, you see it's going to simplify it like this. So it depends on the likelihood, it depends on the prior, but the denominator canceled out. So we don't need to worry about calculating that in order for running this Markov chain. All we need is the likelihood and the prior. So that's very cool, very useful. this is just going through, again, very simple example of how this works with our simple random walk. Like if our target distribution pi was uniform, now of course we can easily sample from a uniform distribution, or we could run the Markov chain so that it has uniform distribution. But let's pretend we can't do that. The only thing we can do is we can run this Markov chain KP, which takes steps to the right with probability P. And then we're going to change this KP to give us uniform distribution. So I will just not go through everything, but it's just simple algebra calculations. And then you get this new Markov chain, which is symmetric and has stationary distribution uniform. So any Markov chain you can change however you'd like. Of course, there's practical considerations for a real problem. Like how many steps do you have to run before it reaches the stationary distribution? And also, does this depend, the number of steps depend on the choice of proposal, Markov chain K? And those are difficult questions to answer in practice for a specific example, but things to keep in mind. Okay. So I think just to wrap up, a little summary of what I hope you'll take away from this talk is, yeah, I hope you know what a Markov chain is now, and I hope you're excited to learn about other Markov chains. They're special random processes with very nice properties. They're applied in many cases, used to model a huge range of random behavior. And we talked about this one application useful in statistics for sampling from a posterior distribution, or whenever there's a distribution that you want to sample from, you can design a Markov chain using the Metropolis Hastings algorithm. Okay, and I will stop there, and hopefully we have time for a question or two.
Absolutely. Thank you so much, Mackenzie. That was a wonderful presentation. And what I'll just note also is that what's so spectacular about this research, especially on Markov chains, is the number of applications. Mackenzie touched on a few of the many ones, such as card shuffling or genealogical trees. Something else that's interesting is that you can even imagine web pages on the internet as nodes on a graph. And the transition probabilities are then the likelihood, say, of navigating from one page to another by clicking a link. And thinking about the internet in this way is actually the foundation of what's known as the PageRank algorithm, which was used and developed by Larry Page when he was starting Google. So this is so important, and understanding the mathematical foundations is even more so important as we think about all of the data science applications moving forward. So thank you again. In terms of questions, we had one from the chat about a specific slide. I believe it was for card shuffling, adjacent card shuffling. So maybe if we could look at that one. And I think it was actually towards the very beginning for Markov chains. The participant was wondering where exactly the 1/5 were coming from in terms of the stationary distribution. So maybe you could talk about that a bit more.
So is that two separate questions? First about...
Yeah, so I think the first, I think it was a slide that the participants referencing towards the very beginning when we were showing Markov chains. Yeah, exactly. Yeah, this one. So maybe you could talk more about why exactly are we getting those 1/5?
Yeah, so, well, first of all, this is the uniform stationary distribution. So everything, think about this. This is the probability of one, this is a probability distribution, probability of 2, probability of 3, probability of 4, probability of 5. Everything has the same probability and it sums to 1. So it's a distribution. So why we get that in this exact case, this specific case, I mean, we could, I kind of scribbled here, but we could write down more carefully that this vector, if we're thinking of it as a vector. So I go back and forth, you know, between thinking about it as a function, a probability distribution, or a vector. Because when it's a discrete state space, we can write the function just as a vector like this. And so if we multiply this by I'll just do like the first row or the first column. So if I do this multiplication, this dot product with this, how you do usual matrix multiplication, I'm going to get 1/5 times 1/2 plus 1/5 times 1/2, which is just going to give me 1/5. So this first entry here is going to be 1/5. And then if you do the same thing for all the other columns, you'll see it's just going to keep giving you 1/5, 1/5, 1/5. So just matrix multiplication, linear algebra, the 1/5, you know, everything the same. Notice though, you know, if I did 1, 1, 1, 1, 1, that would also be a left eigenvector, right? That would also satisfy pi k equals pi, but I need to normalize it to be 1/5 so that it makes sense as a probability distribution. So the 1/5 vector is the unique vector that satisfies this condition where it's a probability distribution, and it also satisfies this condition. It's a left eigenvector with eigenvalue 1.
Perfect. Thank you so much. Something else I'll ask. So you actually anticipated my question about the number of steps taking, the number of steps required for converging to the stationary distribution. Can you speak to how difficult it is computationally to take several powers of this transition matrix K? Like, is it diagonalizable or something, or does it end up being a computational burden?
Yeah, that's a good point. And so that's where being, you know, some Markov chains are nice, and being reversible is related to that. Being reversible is nice. And what I didn't say is if the Markov chain is reversible, then K is diagonalizable. And so you know that if K is diagonalizable, it's very easy to compute powers.
Perfect.
Not all Markov chains are nice and reversible, but usually they are, especially the Metropolis Hastings. That's always going to give you a reversible Markov chain.
Perfect. That's so interesting. Well, let's thank our speaker again. We really appreciate it.